Hello students and welcome to Chemistry B. I'm Miss Slate and today we're going to be talking about intermolecular forces. So let's start by looking at these two graphs. Both of them represent a graph of boiling point versus molar mass for a series of compounds. Let's start by looking at the one in the upper left. We can see a really nice, mostly linear progression of hydrogen to nitrogen to oxygen to carbon dioxide to chlorine, where it seems to be a roughly linear progression of the bigger the molar mass, the higher the boiling point, with an exceptional outlier being ammonia NH3. We see something similar in the second graph, which is also boiling point versus molar mass. There's a very nice linear progression of rubbing alcohol to bleach to gasoline, where the higher the molar mass, the higher the boiling point of the liquid is, again, with an exception of water being an outlier that doesn't fit the trend. So why do these couple of compounds not fit the trend? Well, that has to deal with their intermolecular forces. So first of all, let's talk about what attractive forces hold particles together. So there's ionic bonds, covalent bonds, and these are what we call intramolecular forces. So they're the forces within molecules. They're what hold atoms together to make molecules and compounds. So something like sodium and chlorine are oppositely charged, so they would be attracted to each other, and that is their intramolecular force that holds them together. Again, similar to what we were thinking with the graphs, there's also the question of why are some substances solid at room temperature while others are liquids or gases? What determines what phase of matter something will be in at room temperature? Well, this has to do with their intermolecular forces. So these are the forces that occur between the molecules of a substance. So for example, if we had two sodium chlorides interacting, the negative end of chloride would be attracted to the next positive of the sodium, and that would be an intermolecular force. So like we said, intermolecular forces, those attractions between molecules, are what determine what phase of matter things are at room temperature. If something is a solid at room temperature, it's got very strong attractions between its molecules. If it's a liquid, there's going to be a moderate attraction between the molecules. And if it's a gas, it's going to be a very weak attraction, if any at all. And again, these are intermolecular forces, the forces of attractions between molecules. And there's different types of intermolecular forces. One type of intermolecular force are dispersion forces. Dispersion forces take place between nonpolar molecules. And that's basically because nonpolar molecules, like nitrogen, they don't have like a positive or a negative end to them because the electrons are shared equally between each element. But when two nonpolar molecules collide, those electrons can get shifted temporarily, giving it a temporary positive end and a temporary negative end. Which can cause a weak and temporary attraction between the two nonpolar molecules. So, main thing to remember about dispersion forces is there are forces of attraction between molecules that have a temporary dipole. So we're talking nonpolar substances. And that this is a weak and temporary attraction. So dispersion forces are some of the weakest of the intermolecular forces. Next up are dipole-dipole forces. Dipole-dipole forces occur between polar molecules. So remember, if the atoms in a bond have an electronegativity difference between 0.4 and 1.7, they are in a polar bond. And if the molecule is symmetric in shape, even though it has polar bonds, it would be nonpolar. So nonpolar molecules will experience dispersion forces. But if it's an asymmetrically shaped molecule with polar bonds, it's going to be a polar molecule, which means it can experience dipole-dipole forces. And that's because the electrons in a polar bond are not shared evenly. one atom hogs most of the electrons, giving polar molecules a slightly positive and slightly negative end. And so dipole-dipole forces are forces of attraction between molecules that are permanently polar. The positive end of one molecule is attracted to the negative end of another molecule. So this is a permanent but moderate attraction between molecules. So stronger than dispersion forces, but not the strongest type of intermolecular force. The strongest type of intermolecular force is hydrogen bonding. So it is a strong, permanent dipole-dipole attraction between molecules. But it only occurs in compounds where hydrogen is bonded directly to oxygen, nitrogen, or fluorine. And that's because all three of those elements are very small and very electronegative. So this causes a huge difference in polarity, causing the attraction between those molecules to be very, very strong. So when hydrogen is bonded to oxygen, nitrogen, or fluorine, the electronegativity difference is just so much bigger that the dipole-dipole attraction is like way more than it would be normally. And so that's what we call hydrogen bonding. And that's what accounts for the disparities in those graphs we saw at the very beginning. Remember, it was ammonia, NH3, and water, H2O, both of which experience hydrogen bonding. And so the attraction between their molecules is very strong. So the main thing to remember is the relative strengths of the intermolecular forces. Dispersion forces are the weakest. Dipole-dipole forces are moderate attraction. And hydrogen bonding is the strongest type of intermolecular force. But hydrogen bonding only takes place in compounds where hydrogen is bonded to oxygen, nitrogen, or fluorine. And that's all that we need to know about intermolecular forces.